Hello, welcome to my channel. In this video is the chapter 3 of the dynamic series called the Constraint Motion problem 1. So in this first problem of the concept, we will try to understand how the constraint motion works in the pulley system. Okay, so what you see here is block A that was hanging on this pulley, and the card B that's what at this platform. So if you imagine, if I pull this block B toward this side of the schematic, you can clearly see that point A will be moving upward, right? So in a similar sense, if block B was going to the left side, then block A would have top downward. Okay, so now look at the question is simple. If block B has a leftward velocity, meaning going to the left side here, of 2 meters per second, determine the velocity of cylinder A. Okay, so firstly, block B, like we mentioned, if block B is moving, so if block B is moving toward left side, surely block A will go downward like so. So firstly, in this constrained motion, we first has to understand the kind of how much rope has moving in the motion. Okay, so if B is B moving to the left, meaning that some rope have to go a little bit down, like maybe like this, enlarging, extended, and the other have to go up, something like that. So we will try to understand that constraint by first make a make a reference line from the fixed point. Let's say I make it on this blue line toward block B, and I call this x less than x. Then I did again in the red line vertically. I point from this pulley to this pulley and call it y as a variable. Then I see that the green line here from this pulley and this pulley is a constant, meaning that it doesn't move, it doesn't change during this motion. Okay, so no matter what motion will be, these two, the displacement in the vertical axis here and here will be the same, and I call it B. Okay, then I was trying to measure this distance from this pulley up to this one, and surely it should be y plus b, right? So now the pulley, the rope also covering this curve, right? So in the small small pink arrow, and the pink curve indicate R1, indicate the half of the circumference of the circle in this small pink curve here as a pulley R1. Then in this bigger curve here, we call it R2. This curve also part of the rope, right? So it will be combined with the total length of the rope. Okay, so also this quarter of the curve at R3 is part of the rope and also. So you see I mentioned about the length of the rope, right? So because we will start describing the motion by the length of the rope. Okay, you see the rope in this system does not stretch or change the length, meaning that the rope will be, for example, if the rope is 4 meters, it will stay as 4 meter length of rope. It does not change it like longer or shorter. What change is the motion that rope is attached to. Okay, so in order to determine velocity A, you first have to dive into the simple concept of the rope that does not stretch or compress during this motion. So we then assign the total length of rope equal to L as a constant value. Now, that length of rope L, what would be the value? Okay, so first it would be equal to x, this length, plus y, this length. Okay, it may be better if I change the color. Let's see. Okay, this one. So it will be x. Okay, it will be x here, plus y, which is this, plus y plus b times 2. I believe is this line and this line as well. Then plus the curve of each one. This curve, R1 is this curve here, R2 is this curve here, okay, and then R3 this curve here. Okay, you can notice that the blue line I drawn is cover all the length of the rope, right? So now this equation is complete. Imagine if I differentiate this equation, what it will be. Surely constant differentiate will be 0, right? And all part of this will turn into 0. Reason is simple, because pi is a constant value, and R1, the radius of the pulley, is also doesn't change. So differentiate those will be turned into 0. Also b will turn into 0. With that being said, we got this relationship. 0 equal to x dot plus 3y dot. Then if we rearrange, we'll get that x dot equal to minus 3y dot. And since it's given the velocity of the b is 2 millimeter per second, but it's in leftward direction, you see that it goes against the direction of the x I tried to describe, meaning that if I substitute 2 meter per second in x dot, it should be minus 2. So I substitute that, we get that the minus 2 equal to minus 3y dot, and then finally y dot equal to 0.67 meter per second. Now, if you look closely, I assign y as a downward direction as positive. So if it go with positive direction, meaning that the card A is going downward. Okay? And this is the solution of this problem. Okay. Thank you so much for watching. This new concept is very fun and interesting to solve. I hope you learn how to solve this constraint motion with the fundamental I try to give in this video. Thank you so much for watching. See you in the next video.